we have been having a series of lectures on systems of particles and rotational motion. In the last lecture, we asked the following question: what is the rotational analog of mass? And we found that this is the concept known as moment of inertia, and we calculated moment of inertia for various objects like circular ring, rod, sphere, cylinder, and we also discussed two important theorems, the perpendicular axis theorem and parallel axis theorem. Now we will proceed further. It is almost that we have all the necessary concepts and techniques that are required to study the motion of a rotational motion of an object, and essentially we are going to focus on rotational motion. Rotational motion about a fixed axis. This is a simpler form of the problem of in rotational dynamics. We need to study both kinematics and dynamics. Kinematics means the study of motion without any specific reference to the forces which are acting on it. Okay. Now we are, as I told you again, we are going to focus on rotational motion about a fixed axis. The advantage is such a motion requires only 1 degree of freedom. What is it? Suppose I have here an object, and then I have here 3 axes: x axis, y axis, and z axis. And so an object, every particle, it will go around in a circle. So what happens is, this is the axis going down, and originally the point P is here. Let us say now it comes to P prime. So it makes an angle. This angle is theta. So the location of a point can be specified by just the angle. This is a fixed axis. We need to keep this in mind. Just theta alone is sufficient to specify the position of the particle. And first we will study kinematics, then we will go on to dynamics. And we already have, this is theta is the angular displacement, we know. This is the angular displacement. Theta is the angular displacement. We have this quantity is angular velocity, or it has got another name, rotational speed. Angular acceleration alpha is d omega by dt. Okay. So in the case of linear motion, we have the case of linear motion. The case of linear motion, the kinematical equations are V is equal to U plus AT, and S, namely the displacement, is equal to whatever the initial displacement plus ut plus half AT squared, and then V square is equal to U squared plus 2AS. The symbols are all very standard. U is the initial velocity of the particle, V is the velocity at that particular instance time, A is constant acceleration, uniform acceleration, then S is the displacement. These are all fairly standard things. Now the corresponding kinematical equations in the case of rotational motion, are, we will write down omega is equal to omega naught plus alpha t plus theta is equal to theta naught plus omega naught t plus half alpha t squared omega squared is equal to omega naught squared plus 2 alpha theta. How are we getting this equation, sir? Is it just by analogy or is there any methodology? And you can see that at the outset there is a remarkable similarity, okay, between linear motion, kinematical equations of linear motion and kinematical equations of rotational motions. How are these equations arrived at? First thing we need to remember is alpha is a constant. Okay, so first we start with the definition of d omega by dt is equal to alpha, which is a constant. Therefore integrate what do we get? If I integrate, I will get omega is equal to alpha t plus c. I am integrating between 0 and c, 0 and t, let us say that. Then at time t is equal to t naught, at t is equal to t naught, t initial, let us say omega is equal to omega naught. Therefore this implies c is equal to omega naught, and hence I have the relation omega is equal to omega naught plus alpha t. Okay, so this is the first equation. I will write here. Okay. So from this I will make use of it later, omega minus omega naught by alpha. I will integrate. What is d theta by dt? D theta by dt is equal to d theta by dt is equal to omega naught plus alpha t. Okay, then again I integrate. What will I get? Theta is equal to omega naught t plus alpha t squared by 2 plus a constant of integration, c, a constant, c, a constant. It's a constant of integration. Let us say that at theta, at time t is equal to 0 is theta naught. So therefore I will have theta is, when I put that, what will happen? This implies c is equal to theta sub naught. Therefore theta is equal to theta naught plus omega t plus alpha t squared by 2. This is the second equation of motion. This is second. This is the third. So what did we do? This for second one, d theta by dt. This is where we started. Omega is d theta by dt from that definition, and right. Then now what we need to do is, this is the equation 2. If you eliminate from these two equations t, okay, so that will leave it as a simple exercise. We will not do it, rather eliminate t between 1 and 2. You can do it as a simple exercise, and you will get here omega squared is equal to omega naught squared plus 2 alpha times theta minus theta naught. Okay, so this is the third equation. Only thing you will find that when I wrote here third equation, you will only have 2 alpha theta. Of course, it does not, I can't say it does not matter. What we have is a time t is equal to t naught, theta is theta naught. In this particular equation 3 here, at time t is equal to 0, theta naught is 0. That's all the difference. However, both these equations have the same spirit. So, what we realize from this is, following. From these two kinematical equations, you look at it, the role of v is taken over by, the role of linear velocity is taken over by omega, and the role of displacement is taken over by angular displacement. The role of linear velocity is taken over by, the role of acceleration is taken over by alpha. So this is the kind of correspondence we have here. Yes, correspondence. The role of S is taken over by angular displacement, linear velocity is taken over by omega, and then the linear acceleration role is taken over by alpha. Okay. Now we have some comments here. You take a look at this equation. See, each of this, the first one is the definition of velocity of the particle at any instant of time. This tells you how to calculate the distance traveled. What does this equation say? This we are going to come across little later. Now, I will take this particular space. What I will do, v squared minus u squared by 2 is equal to a into s, right? Displacement. Multiply by m on both sides. So v squared minus u squared is equal to ma into s. What is that we have on left hand side? It is the change in kinetic energy. If the initial velocity, if the velocity is v and then it get reduced to u, this is the drop in kinetic energy, and that must go as the work done on the particle, that is by the force. M into a is force into distance. So this is the so-called work energy theorem. We are going to come across the rotational analog of this little later. Now we have the we want to relationship between angular and linear quantities. Next topic is relationship between angular and linear quantities. To some extent we have seen this in lecture 3. However, we will have, so what we have is we have a rigid, we have an object which is going around. This is the axis, x-axis, y-axis, and I have here, let us say this particle is I consider circular motion of a particle. This is r, this is theta, and this is the linear velocity v. We have the standard thing, v is r omega. Actually what we have is in vector form is, we have seen it in lecture 3, omega cross r. So this particle is moving on the circular path. At this instant the angular displacement is theta. So what is v? V is, by definition, it is ds by dt, rate of change of displacement. Right. So we want to calculate ds, which is this arc length, which is nothing but r times d theta, whatever is the change of angle, by dt. Very simple. ds is change in arc length, is change in this angular displacement, that divided by infinitesimal, and take the limit. Okay, therefore v is r into d theta by dt. Now tangential acceleration. Tangential acceleration So let me draw this diagram in a better way. This is some rigid body, and I have the axis, x-axis, y-axis, and so I am considering the circular trajectory of a particle. So at this particular point, the tangential acceleration will be like this: a sub t. I am using the same symbols as one which I used in earlier one, in lecture 3. This is the radial acceleration, and if I compound these two, I will have this quantity is actually the I will call this as p, and this as q. So PQ vector is the actual acceleration vector, which earlier I have called it like this in lecture 3. No problem. So the tangential acceleration is equal to this is the linear velocity in this direction, therefore it is dv by dt. This is equal to d by dt of r omega. This is r into d omega by dt, which is r alpha. This is what earlier we called it as alpha cross r, which we called it as capital A r vector. Okay. Now radial acceleration. There is an acceleration in this direction towards the center, right? This we must have. There should be a centripetal acceleration, otherwise we cannot keep the particle going around the circular orbit. So AR is equal to V squared by R. This is the standard formula for centripetal acceleration. This is equal to R omega whole squared by R. This is R omega squared. What is R omega squared? Omega is d theta by dt whole squared. This is what earlier we called it as R theta dot squared. Remember, what is theta dot? D theta by dt. Now, earlier we had in lecture 3 this formula. AR is minus R theta dot squared times ER. You may ask me, what is this minus sign, sir? Now we are not having. Please remember, it is minus ER. That means, if this is the ER direction, unit vector, minus ER is towards this. So, this is, if ER is this direction, then minus ER is in this direction. So what you have is the magnitude, so it is fine. Now we have the we have the tangential acceleration term. We have the tangential acceleration term. Here I should have written t, which sorry, and we have the radial acceleration term. Therefore, we can calculate what is the actual a, which we wrote it as earlier. So actual a is equal to, which in our earlier notation is this. So I will put it in inverted commas, is equal to AR unit vector ER, the radial component of the acceleration, tangential component of acceleration, theta. Right? So therefore the magnitude of the vector A acceleration is equal to AT squared plus AR squared R alpha squared plus R omega squared whole squared. This gives you R times alpha squared plus omega to the power of 4. This is the magnitude of the acceleration of a particle which is moving in the circular orbit. Now, the advantage of studying rigid body about a fixed axis is that in a plane perpendicular to the fixed axis, every particle goes round in a circular motion. Next is, we have to ask an important question. There is a concept called torque which we had introduced and studied, and there is something called angular acceleration. What is the relationship between these two objects? So this next one, there is a relationship between torque and angular acceleration. It's a very important topic. So we'll we'll see that the angular acceleration is alpha. It is a vector quantity generally. So we will see that first we discuss the case of particle rotating about a fixed point under the influence of an external force. Then we extend the results to the case of a rigid body rotating about a fixed axis. First we consider a particle which is going on a circular orbit. There is a tangential force. This is radius is r. This is radius is r. Yeah. And then there is a mass m. Here it is the tangential force. Tangential force. So there must be a centripetal force, otherwise it will not move on the circular orbit. As we stated earlier, it is necessary. I am not indicating the existence of f of r. It must be there, otherwise you cannot keep it in. You cannot keep the particle moving in a circular path. And so the tangential force gives rise to tangential acceleration. And so the tangential force Ft, the magnitude, is equal to mass times tangential acceleration. So the torque about the origin due to the force Ft, the torque. This force acts on the particle. Therefore, I can talk about torque on this particle about this particular center, namely the origin. And torque about the origin due to force Ft. Tau is equal to, I am writing only the magnitude because these directions are perpendicular, Ft times r. this is equal to m into at times r. Okay, now what is at? In the earlier section also we calculated, it is r times angular acceleration. With this we know. In the last section also we calculated. Therefore tau is equal to mr squared into alpha. Okay, so this is same as, what is mr squared? Moment of inertia times alpha. So we have this important relation. This is for a particle which is moving due to a tangential force, and then there is a centripetal force to keep it on a circular path. Tau is equal to I alpha. In other words, we say that the torque acting on a particle is proportional to the angular acceleration alpha. Therefore I is the proportionality constant. So I is proportionality constant. இப்போ எழுத மாட்டேங்குது, என்ன பண்ணீங்க? டிசேபிள் பண்ண சொன்னீங்க, எழுதலையா? வாட் எழுத மாட்டேங்க. Okay. This is the rotational analog of Newton's second law, F is equal to ma. Now we extend the discussion to a rigid body of any shape but rotating about a fixed axis. So now we extend this discussion to rigid body of any shape but rotating about a fixed axis. So I have some arbitrary rigid body and I can set up the axis. O is the origin and x, I have here a small mass dm. This dm will sweep a circular orbit, and this is the tangential force. The tangential force is dft. Okay, typical mass element is dm, this is r. Okay, so I have this dft, I am writing only the magnitudes. Dft is equal to dm times mass times tangential acceleration. Now I can calculate torque d tau. I am writing parallelly here by the side, therefore you can compare. The torque d tau due to the force dft about the origin. Is equal to d tau is equal to r times dft. So the direction of force and r are perpendicular, therefore it simply goes to this. R times, what is dft? Dft is dm times at, a sub t, tangential acceleration. And we know what is tangential acceleration is r alpha. Therefore it is Therefore it is r dm into r alpha. This is equal to alpha times integral r square dm, right? This is for tau. So this implies tau is equal to I times alpha. Strictly speaking, I should write in a more generic way, tau is a vector, it is proportional to alpha vector, then the constant of proportionality is, it can be, this is the moment of inertia times alpha. When you go for higher studies, you will realize that in general tau is proportional to alpha, and then I is not simply a constant, it will be a 3×3 matrix. Now, right now we are not concerned about it. And now we will come to perhaps the most important equation we have is, this is something similar to linear motion. F is equal to m times a. So force vector is proportional to the acceleration vector. The role of mass is to play that of the constant of proportionality. Here the moment of inertia plays the role of the constant of proportionality between tau and alpha. Now we have one more thing to do, namely, what is the relationship between, what is the role of work and energy in rotational motion? Work and energy in rotational motion. Okay. What is the definition of torque? Torque is defined as R cross F. What about the dimensions of torque? It has that of work or energy. However, it's a vector quantity, so the torque can rotate an object by so if a torque can, when a torque is acting on a body and it rotates the object, rotates the object about an axis, let us say by d theta, then the infinitesimal, the work done for this infinitesimal rotation is then the work done for the infinitesimal rotation, for this infinitesimal rotation is, what is that, d tau is equal to, sorry, work done, no? So dw is equal to tau d theta. So this is something similar to in linear motion, f dx. This is the analogy. In linear motion, f times the force acting on it, it moves it by a small amount dx. So here it is the torque, so it rotates the body by d theta. Therefore the amount of work done is infinitesimal rotation is tau times d theta. Now I can calculate d omega by dw by dt, sorry, dw by dt, rate at which the work is done is equal to tau times d theta by dt. D theta by dt is omega, therefore it is tau times omega. So what is this quantity? Rate at which the work is done is the, what you call it as, instantaneous power. What is the rate at which the work is done? That is what you call it as the power. And so I have this, we have this power is equal to tau times omega. It's a scalar quantity. Now we can ask, what is the corresponding equation in linear motion? What is the corresponding equation to this in linear motion? I should not put in linear motion, I'll put it. Power is equal to, yeah, if I differentiate, this will be d by dt of, this will be the, with the, it will be f into v. Okay. So you can see that there is hardly any distinction between linear motion and rotational motion with respect to either kinematical equations or dynamical equations. There is a one-to-one correspondence. Now we will have, there is only one thing which is left out in the last lecture. Okay. See, in the last lecture we had seen the so-called work energy theorem in the case of, when you look at the kinematical equations. I hope I have it here. If I have it here I can show. I'm not sure if it is not there. Yes. This particular the last kinematical equation, v square is equal to u square plus 2as. This is what we call it as the work energy theorem in the linear motion. Now we would like to give a similar interpretation in the case of rotational motion. And what is it? Right? Work energy theorem. Work energy theorem. Let me write little better. Work energy theorem in rotational motion. Okay. So where shall we start? We start with, we have tau is proportional to alpha and constant of proportionality I. This is the basic equation. So this is same as I into alpha is d omega by dt, rate of change of angular velocity. This I can write it as a little bit of calculus, chain rule, d omega by d theta. We want to bring in the basic variable angular displacement, it is dt by dt. This is what you call it as chain rule, I times d theta by d theta omega, and I will have d omega by d theta. So we have, now I bring the d theta to this side, so I have tau times d theta is equal to, tau times d theta is equal to into I omega d omega. But what is tau times d theta? Remember, this is the torque tau acting on the body induces an angular displacement d theta. Therefore, it is the amount of work done by the torque in rotating the body by d theta. Now we can integrate on both sides. On both sides, we get the integral tau d theta. This is from theta naught to whatever point theta. This is equal to theta naught to theta I omega d omega. This is I omega squared by 2. So what I will have is I by 2 omega squared by omega naught squared. So what is that? When the particle is at theta naught, theta, what is theta minus theta naught? That is the change in angular displacement. It is the change in angular displacement. Okay, when the particle is at theta naught, the angular velocity is omega naught, when the particle is at theta, the angular velocity is omega. Therefore, the corresponding angular displacement, corresponding change in angular velocity is given by omega minus omega naught. The corresponding change in angular velocity, angular speed rather. Right. Okay. So what I have is this is the work energy theorem. So it is something like the change in kinetic energy. What we have is this is the you can compare this with particle kinematics, a particle moving having a linear motion. The corresponding equation is what? Corresponding equation is the work done is m by 2, sorry, I forgot to write this, v squared minus u squared. This is in linear motion. Linear motion. Okay. So this is the so-called work energy theorem. In rotational motion. Now we have to do, we have introduced almost all important concepts. Now we can compare the similarities between rotational motion and linear motion. So I will have here on the left hand side I will have rotational motion. Here we will have linear motion. One, what are the various quantities? Angular velocity. What is the definition of angular velocity? d theta by dt. This is also denoted by theta dot. Now 1. In the linear motion, the role of theta is taken over by x. Therefore, linear velocity is v is equal to dx by dt. Then angular acceleration. Angular acceleration is alpha. This definition is d omega by dt. This is also theta double dot. Here linear acceleration. Here means in the corresponding situation in the linear motion is linear acceleration is a is equal to dv by dt. Of course, I am doing in one dimensional, no problem. We can extend it to general case also. Now, torque. Tau is equal to I alpha. Since we are considering mostly the rotation about a fixed axis, that's why I am writing it. Otherwise, I need to put proper vectors. So in this case, linear motion, force is equal to F is equal to m into a. Remember, we had seen moment of inertia takes the role of mass. The role of mass in linear motion is taken over by the moment of inertia in the rotational motion that we had seen. Actually, we are summarizing whatever we have done so far in a sense. Kinematic equations. Omega naught plus alpha t. 4. There are several. What V is equal to U plus AT. Then next is theta is equal to theta naught plus omega naught t plus half alpha t squared. Here it is S is equal to some initial displacement which is already there in the system for the particle Vt. S is equal to ut, sorry, it is not ut plus half a t squared. Then finally omega squared is equal to omega naught squared plus 2 times a into theta minus theta naught. Here it is v squared is equal to u squared plus 2a into s minus x naught. Then in a sense this equation is what you call energy conservation. Okay, this is also rotational energy. Whatever loss in rotational energy, this must go as a work done. Then 5. What is the work done? Expression for work done is tau is the torque acting on the body, infinitesimal displacement is d theta, therefore this is the amount of work done in shifting by d theta, therefore total work done is from a particular value to particular value. Now here in linear motion case, work done W is equal to, this is a one dimensional case we are writing here, fx into dx, x naught into x. In general case, force is a vector that should be dotted with the displacement vector. Then sixth one, kinetic energy, expression for kinetic energy, half I omega squared. Now in the case of linear motion, kinetic energy is equal to half m v squared. There is one more equation which I will write, but its derivation we will see in the perhaps maybe next lecture. Before that, we will have the power. The power P is equal to tau times omega 7 power P is equal to force times velocity. Then 8th one. சார் அடுத்தது போகணுமா இல்லை அப்படியே கண்டினியூ பண்ணலாமா?
சார் நெக்ஸ்ட் நான் இப்போ எத்தனை இருக்கு சார்?
நெக்ஸ்ட் ஸ்லைட் அப்படியே கண்டினியூ
பண்ணலாம் சார்.
இதே கண்டினியூ பண்ணலாம் இல்லையா? இங்கே எழுதலாம் இல்லையா?
எழுதலாம் சார்.
8. So this is the equation which I am going to write just to complete the analogy, but we are going to see it little later. It is the angular momentum L is equal to I omega. Here it is linear momentum P is equal to m into v. Since I am dealing mostly one dimensional here, I am not writing vectors, otherwise one need to write. Okay. Then this we will this I will cross it here to show that we will be doing it later. And 9, then tau is equal to this we had seen in the much earlier. How is tau defined? dl by dt. Rate of change of angular momentum is what known as tau, and similarly the rate of change of momentum is what known as force. In a sense, this is the Newton's second law. This is the Newton's second law in rotational dynamics. Okay. Now with this the analogy is complete. Let me quickly summarize what are the things we have done in this first lecture. In this particular lecture, we started with rotational motion about a fixed axis. We had seen the basic. First we did the kinematics, then we moved over to the dynamics, then we took a stock taking. In the case of linear motion, we have v is equal to u plus at etc. the kinematical equations. In the case of rotational motion, we have got these equations. In fact, all these kinematical equations we have shown the derivation. Of course, we always start with a simple definition of we start with the simple definition of omega. The angular speed is d theta by dt. Then relationship between angular and linear quantities. It was earlier done in a different in lecture 3. We are taking a stock taking, and right, and this is the expression for the acceleration. After that we discussed the relationship between tau and alpha, which is a very important relationship. It says that tau is equal to I times moment of inertia times alpha. And this we did at the kinematical level. It is at the level of dynamics. And okay, this is the so-called Newton's equation in the rotational motion. Work and energy in a rotational motion. It is fairly simple. If tau is the torque acting on it and it induces a displacement of d theta, then tau d theta, and we can integrate it. So what we have is the P is tau times omega, and right. This is the work energy theorem. In the case of rotational motion, we have seen that. And then finally we made a table comparing the basic equations occurring in rotational motion with those of equations occurring in linear motion. And it is very remarkable that there is a similarity. There is an exact similarity between these two, and we will stop at this stage.